Okay, so good evening, good morning, and good afternoon, everyone. I hope you all know what this session is going to be, right? First of all, I would like to thank AV Analytics Vidya for organizing this, right? And also to the people who are here, right? We are going to understand a lot of concepts today related to diffusions. Yeah, so let's get started. Okay, so I hope you can see the screen, right? Yeah, so we are going to cover about diffusion. But before we go into diffusion, there is something that we want to know, like what is diffusion and why do we need to study it? The reason for that is since we have seen the advent of different generative art forms, mainly different art forms or different videos which seem to be surreal, right? These are all generated using artificial intelligence. But when we go down and look into depths about how these are created, then we'll be finding that these are nothing but simple models, right? Working or trying to minimize certain latent spaces, right? So I did not want to create any PowerPoint presentations because that is very cliche. So I wanted to deep dive into the concept with some, let's say Notepad, for example, so that, or not required Notepad. I think a simple paint will do the trick, right? So that you can understand the topics quite well. So from what do we know about GANs? So we know that GANs are nothing but kind of a minimax game, right? Where you have two components, generator and one of a discriminator, right? So adversarial training, right? We have a generator and a discriminator which tries to play a zero-sum game, right? Where the generator is always trying to outsmart the discriminator, right? Now we have seen that GANs produce different kind of beautiful images, right? We have seen generative art forms for cycle GAN, DC GAN, different kinds of convolution backends with GAN, right? And also the different style GANs that we have in place as of now. But there is a drawback of GANs in the form of the GANs being too heavy for any hardware, right? Any hardware to compute, okay? And the second thing is that convergence takes a lot of time. Now, I can ask you a question. This is a quite popular question which are asked in interviews, right? So how can you say that GANs converge way slower than any other discriminatory model, transfer learning based model? So you can say that, since GANs always play a minimax game, right? So the generator is always trying to take advantage of the log loss of your discriminator and vice versa. And in that case, this conflicting ideologies of generator and discriminator always creates a kind of lag in the convergence. Okay, so that is why GANs are quite, I would say, first of all, they are hardware heavy. Doesn't matter if you use PPUs, GPUs, it is still hardware heavy. And for large image sizes, large batch sizes, you are going to have a quite large, training time. Although the generalization is quite, fair when we use the modern versions of GAN, let's say style GAN or something like that. But still, it's still in the initial stages. If you train for 50, 60 iterations, then in that case, it is still a little bit, may not give you good results. So we come to another part where we can think of how can we, extend this GAN concept to build something better. And actually, the concept of diffusion comes from there. I think many of you have heard of autoencoders, right? May have heard of, or may have AEs. Okay. So what can you think of? What do you think that AEs are? Autoencoders. They are a kind of a funnel, dual-sided funnel model, right? Kind of like this, right? Where you pass in an input latent space or an input image with the hopes of reconstructing the same input image, right? So let me see the chat. So let me zoom my screen. this is quite visible, I guess. For this, let me zoom in so that you can see. Thanks for the heads up. So yeah, so in the case of autoencoders, we are trying to reconstruct something. Given an input latent space, we are always trying to reconstruct something. But there's a discrepancy in that. How do we reconstruct something that has already been, that we are getting a distribution from? So let's say we have an input image, but machines does not understand that as an image. Machines understand that as a distribution. So how do we sample an output distribution provided given an input distribution, right? So that is a very complicated, mathematical problem, because you may not know what is the other, like the noise distribution that is there. So that is where variational autoencoders come into the picture. Variational autoencoders are nothing but introduce some amount of noise into your dual-sided funnel model, right? So that the model can, perform backpropagation more efficiently to generate or reconstruct the input latent space. It is just like adding, let's say, a catalyst to your chemical reaction. So you want to regenerate something, right? So instead of adding positive samples, try to add some negative samples into it. And that is the concept behind variational autoencoders, which are, let's say, single variational autoencoders. And I found a good blog which was explaining this. First of all, this is Lillian's blog. It is quite mathematical, and I won't go into that details in depth. So if you have time, you can just go through it. But I will be sharing, all the resources are there in the GitHub. But I will be sharing another blog, which is quite good for you to understand and, grasp the concepts. So what happens is that, when you have a kind of a variational autoencoder, right, you are provided with an input sample. Okay, so that input sample is, let's say, any image, right? Any image that you are getting as an input, right? That can be, that is generally conditioned as a probabilistic distribution given your hyperparameters, or given whatever your hyperparameters are. These hyperparameters are, in turn, mathematical sense, these are considered as noise. So this P of theta x given z is your latent space of your input, right? Which we are trying to synthesize or reconstruct using variational autoencoders, right? Now we have our P theta of z, which is our noise sample. Now generating this distribution for noise, it is a little bit tricky because, mathematically we cannot see this. The reason, because this is your input sample space provided, conditioned on your, let's say, your noise, and this is the noise distribution. Selecting this part is one of the trickiest problems in statistics, right? So what does variational autoencoders do? The interesting part is they select another conditional model, which is known as Q of phi, right? Condition the noised variable on your input latent space. Okay, so why this is required? Because since this is difficult to generate, I can multiply and divide this particular value, right? This particular value is nothing but a distribution of your noise provided your input, conditioned on your input latent space. And this is the entire trick which is driving diffusion. Right? So this is kind of a workaround, an alternate pathway. So let's say you, in a chemical reaction, you do not have the catalyst. So what you do, you take another reversible reaction, right? And you take the agent from there to use as your catalyst in your forward reaction, right? So this is just, I would say, a kind of a reversible workaround to this. And this particular equation is actually the driving force behind any diffusion model that you see. Okay, so nowadays you have so many complex models, right, where you take a prompt and you generate an image, you generate an audio, you generate a video and whatnot. So all of these are driving on this particular equation. This is the fundamental equation of any kind of diffusion networks, right? Now, when we move ahead, apart from this, always remember that when we are trying to reconstruct something, reconstruct an input latent space, right? Two things happen, right? We have to adhere our output latent space, or let's say in other words, our output image, as close as possible semantically with my input image, right? Because otherwise it will be two different images, right? Which is not the case. So we need to have the output image resemble the input image. So whenever you want two statistical distributions to resemble one another, you try to measure something called as a divergence between the two, right? So eventually, let me summarize like what we have learned so far, right? Let me just write that in a notepad so I'm just telling you the concept so that it will be easier for you to go through the flow. So in this case, two things we have learned. In the case that GANs is primarily a 0-1 sum game, right? Which can be used to generate a good amount of images and whatnot, right? But at the expense of your hardware and also your training time, right? So this is that is why GANs are, although they are popular, right? But you have to train it for an extensively large period of time. So what are the alternatives, right? So autoencoders are nothing but a kind of a funnel-sided structure used for reconstructing your images, reconstruction of input latent space. I'm writing as LS, right? So this autoencoders also need to, in order to efficiently train them, what we do is we plug into some, let's say the third part is VAE, where we plug in some noise. We input some noise in your conditional variable, in your conditional probability, right? Conditional probability of your input latent space to generate or to generate the output sample, which is as close as possible to the input sample. So in other words, we add some noise generated on your conditional probability. Let me write it as conditional probability on INP on your input sample to generate your output, right? So, and one of the important conditions is that the output should resemble the input. So that means the divergence between your output and your input should be as minimum as possible, right? And I'm sure some of you, if not many of you, have heard about one of the most popular divergence algorithms used in statistical training is that KL divergence, right? I guess this is when you have two statistical distributions, you need to have, let's say P and Q, you can measure the KL divergence constraint by using this equation. And just like I said, the way single-sided variational autoencoders work by introducing noise, right? Conditioned on Q of your noise provided your input sample by multiplying and dividing it, right? Which we saw. And that is the reason why this equation is very important. And this is actually known as your reconstruction loss, right? When you apply log, right, you have a reconstruction loss. And then comes your, I would say, iterated autoencoders, iterated VAEs. So there are other terms like, hierarchical variational autoencoders, which is nothing but iterating over different latent spaces. Now, this is quite interesting. When you consider different latent space, by what I mean is that you have an image of, let's say, 3 channels, RGB. So all of those 3 channels are different latent spaces, okay? So when you are applying a, hierarchical, or I would say looping variational autoencoder, right? You can have a kind of a joint probabilistic distribution, which follows this pattern, just like I told you, multiplying and dividing with your Q, right? This is actually the centralized diffusion equation for your, looped variational autoencoders, right? Q, P by Q, right? Always remember that it is Q of phi, right? P of theta by Q of phi, okay? We are trying to sample your output in such a way so that it resembles your input, right? Now you might wonder, if we are generating the outputs to resemble the inputs, where does the generative ability come from? Like when I prompt a text, how does the new textual generation comes into the play? Okay, so the answer to that question is, whenever you're writing a text, right? Whenever you're writing a text, you need to encode that text, right? You need to encode that text to generate what? Your embedding space for your text. Now what happens is that you take a vision model, right? You take a vision model, let's say a very simple ResNet 50 or ResNet 160, something like that, right? And you generate, let's say you have that trained ResNet 50 on your CIFAR or whatever data set you have, and you have the embedding spaces for your different images. So what happens is, whenever you type in a text, let's say an image of a puppy, right? So what it will do, it will first of all generate the embedding space for that text. That means, image of a puppy, right? It will compare that embedding space with the visual embedding spaces generated from ResNet 50, trained ResNet 50, and take up the one which has the closest distance gap, right? Which has the closest distance gap. That distance gap can be anything. It can be Gale divergence, it can be sinusoidal loss, or it can be any kind of inequalities, right? It can be anything. So that comparison of your different embedding spaces gives you something which you actually see on the screen as a generative art form, right? So this is the concept behind using this diffusion to blend in your textual embeddings, to blend in your image embeddings, right? And then converting the distance, reducing that distance, or finding the closest distance measure, right? Any kind of distance measure, divergence measure, or your standard distance measure, anything can be done, right, to generate your final output. And you might wonder that when is this equation is used? So the ResNet 50, which you trained on your CIFAR or whatever data sets, right, it will try to generate latent spaces for certain intervals of time. Why? Because whenever you write in a text, right, that text generates an embedding space, that is fine. What the image will do, right, image embedding will do, it will take each word at a time, right, per time step, and it will try to generate embedding spaces. And as you know, generating embedding spaces from any kind of vision model is quite expensive. It is time consuming, it is hardware constrictive. So you need to find an efficient way, and that is where this diffusion process comes into the play. Okay, so the images that you see on the internet, right, whenever you type in a text, I think, which is taking many of the social media by storm, that happens effectively with the help of diffusion. Now, so that is the concept. Let me, that is most of the theory that you have to learn, right? Let's say looping VAEs plus is nothing but diffusion. There are two things regarding looping VAEs. The first important thing is a forward path. So diffusion has a forward pathway. Okay, it is just like an image over here. Like, let's say this one. You are generating your images for successive timestamps. You are trying to generate your images for your successive timestamps. Now, how these successive timestamps are there? These are coming from your any kind of temporal input sample. What are temporal input samples? Temporal input samples means input samples which are separated by time. This can be your, let's say, your textual image. This can be your video image, your audio image, and whatnot. So now you know that provided an input text, let's say textual image, a textual sample, right? That is actually the vision model is actually generating different, I would say, outputs, latent spaces for every word that you see, for every timestamp. Okay, this is your diagrammatic representation of your, let's say your diffusion models, diffusion VAEs. Okay, so your P theta is your reconstruction, right? Q is your inference. Inference means what is going to be the generated output. So as you know that we are trying to get the inference or my output from your input samples, but since this is a standard training process, right? So you will be backpropping. So during backpropping, we are taking the samples in a reverse manner, right? So we are taking samples from the X0, that is your first time step, input latent sample space, right? And we are trying to generate for each samples, successive timestamps, xt-1, xt+1, xt+2, and so on. So this successive way of generating something is also known as autoregression. So taking previous input sample, generating a new sample, and so on, right? This is also known as autoregression. So you can say that diffusion variational autoencoders or generalized diffusion models, right, are autoregressive models for generating new samples. Okay, so this is the entire concept behind a probabilistic model. So these are linked inside my repo, which I have. Okay. All right. So diffusion models. Okay. Now, whenever we try to generate some diffusion models, right, always remember that we use a Gaussian sample space. Recommended to use a Gaussian sample space to try to get a good amount of reconstruction, right? This Gaussian sample space can be introduced in your torch-short TensorFlow layers. When you build a torch-short TensorFlow simple dense or that kind of layers, you are trying to initialize them with simple, Gaussian or normal distribution, right? So this only adds to how your diffusion process works. So just there is a full walkthrough or a detailed derivation of that, but I don't. But you can read it at your expense. But this is the idea. Now I've also said about this conditional flow, right? Which you have seen over here, even if it is here as well, not here, this one. This conditional flow is also known as Markov chain. Okay, this conditional flow is nothing but a Markov chain. So what we have learned, this is an autoregressive model, which is fine. It takes the conditioned inputs, right, to generate your conditioned outputs, right? And this is also a Markov chain, posterior Markov chain. So all of these are posterior probabilities, okay? And these are priors. These are known as priories. So this is nothing but a simple Markov chain, which is dependent upon your latent input space to produce a output space, right? So that is what a diffusion model is. Hamming loss, if an embedding C phi is an inverse of C theta. Very good question. So since Jensen, so not only Jensen, so Jensen is for the lower bound, right? So whenever you have a Hamming loss, any kind of loss function, right? Hamming loss means a simple, I guess, point-to-point loss difference, right? So in Z of phi and the inverse function of Z of theta. So, it would not have any effect because the standard VA is the Jensen inequality is just for keeping a kind of an elbow, right? So let's say a lower bound, right? So your constraint, when you apply log on the dual side of your Jensen inequality, right? You are effectively just nurturing another concave function because your log is always concave. Always remember that. So this Jensen inequality is nothing but keeping a lower bound of your input samples given your noise, what you add. So this VAEs will be able to reconstruct properly. There won't be any issues. Now it does, just like I said, it does not matter what kind of loss you use, what kind of distance measure you use. You can use any kind of distance measure, whatever you know of. Even sinusoidal will work. So in the real space, I'm assuming you are talking in the real space. So in the real space, there won't be much of a difference. The VAEs will function, as normal. Okay. I hope that answers your question. Very good question. So now let's go into some coding part, right? So this is a sample which is there in my repo, right? Actually, this is a very critical concept and topic, right? And I know you will have a lot of questions and a lot of doubts when you after this session, because 1 hour honestly is very small for understanding diffusion concept. But I hope you got an understanding or a global view of what diffusion is. Always remember that in chemistry you know diffusion, right? Diffusion and osmosis. What does diffusion do, right? So any kind of fluid at a higher concentration fusing through any kind of orifice with a constant velocity, right, to a lower concentration space, right? Now the same thing happens over here. Instead, you are diffusing your final latent space at each time step, right? At each time step of your input sample to produce your corresponding output. Okay, so think of it in that manner. It will be easier to understand. Yeah. So this is a repo which I created, right? Data over diffusion. This has been taken from F. Cole, from F. Cole's diffusion TensorFlow, right? Implementation with certain changes which I made so that you can understand it better. Now, before I go into the code, you need to understand something. You have understood the concepts and everything, but let me go through the flow again of what this is happening. The example will work, but let me go through the example only. So in this case, what we are doing, so there are different kind of diffusion models. Now, when we talk about diffusion models, let me create a chart for you so that it will be easier to understand. So let's say this is diffusion concept D. Okay. Now inside diffusion concept, you can have different kind of two broadly classified sections. One is unimodal and one is multimodal models. Okay, both of them are using diffusion concept. What comes under unimodal is any kind of unimodal autoencoders, VAEs. Okay, any kind of quantized GANs. Like let's say one quantized GAN is, any kind of variational form of quantized or VQ GANs, in other words, right? So this style GANs, I'm writing as is okay, style GANs. So these are all your unimodal kind of diffusions, right? Now, when you come inside multimodal models, right, you already know that there are many multimodal models, right? You have Clip, you have DALL-E from OpenAI, you have so many things, you have Imagen from Google, right? All of these are diffusion multimodal models, okay? So what are multimodal models? You have two different inputs, two or more input samples or latent spaces, right? And you are trying to do an output of two or more of your output sample spaces, right? So in that case, you are going to have certain models like Clip. This includes, in general, this includes any kind of multimodal transformers, MMTs. So I hope you know what transformers are. Quite popular. I think it is by default, everyone should know or should have, should read. Attention is all you need paper. So that is actually what is driving today all the models that is there. So any kind of multimodal transformers that you see, let's say speech, audio, video, vision, whatnot. Okay. So Clip, DALL-E, and the models which I mentioned, right? Glide from OpenAI, Imagen, text to image that we're going to see, and whatnot. So all of these multimodal models are part of diffusion process. Okay. So this is a broad idea. Now we are going to understand this part today. We have already had a high level overview of what diffusion is, but now we are going to understand this entire flow. Okay. So in this case, we are going to look into text to image. What is text to image? Text to image is a popular model by Sol, right? Who said that, if you can diffuse your output latent space by taking samples from your input texts, right, at each interval of time or time separated, you can generate any kind of art forms, right? And what is going to be the backbone of your image? Your backbone of your image net is going to be, or your image network is going to be any kind of transformer based. It can be vision transformer. It can be, residual block with cross attention layers, any kind of variation of your, any kind of variation of your image model with transformers, right? So he went ahead with UNet. UNet is a vision model or a transformer model, which uses something called as a Swish transformer. Okay, so we'll be going into that code just 2-3 minutes after this. So uses the transformer to generate that embedding space for each time step. And this text to image, what it does is it tries to apply from the input latent space, right? From the input embedding space. So you have the P of theta, right? You have to generate that Q of theta, that noise, Q of phi and Q of phi in the numerator and the denominator. It generates that for every time step, and it tries to give you an output sample. Okay. Now, this is the interface. I've kept it the same as FPolase so that it can be easier for you to understand. You can just go through his repository as well. I have linked to that as well. But let me go through the code. Okay, so let's first start with what an autoencoder looks like, right? A simple autoencoder. So just like I said, an autoencoder has an input and an output sample. Okay, so and what you do with the logic of the input is up to you. You can just keep a simple convnet and you can just say that it is fine, or you can just add some simple attention mechanisms on top of it as per your choice. So I added an attention block to the autoencoder model. Okay, so attention is nothing but always remember you have three matrices, right, which you want to multiply, right? So you multiply your query and your key matrices, right? You perform some mathematical optimization on it, like let's say square root or something like that. You divide it by your, you take your softmax of that and you divide it by your values, right? So the reason why we do attention is to focus just like we do in text, right? So that we can focus on small parts of your latent space efficiently, right? And these query queue and value matrices are very important to generate a good latent space or latent representation over your standard convolution model. Okay, so that is what this call function does. It is just a basic attention block. You see q multiplied by k, which is your query and your key matrices. You do some of square rooting. Generally, it is root over, right? You apply the softmax and then you divide it by your 1 by v, right? So that is generally the way how it happens in the case of attention. Now, what I'm trying to do here is I'm trying to create a kind of a autoencoder, right, which does attention, and I'm going to use this autoencoder to generate my reconstruction sample, right? I'm going to use this autoencoder for my reconstruction sample. Now, let me go back a little bit so that I can make you understand, like, where does this come from? Let me see if they have this big equation. So yeah, so this is actually the loss of your big loss of your entire, what should I say? What we are studying now, diffusion models. Okay, this is actually the loss of your diffusion models. Okay, so this part log p0 x naught given x1, this is your reconstruction loss. Okay, these two are known as your KL divergence terms. The reason because we are, as we know, that we are trying to generate our successive time steps, right? Using this particular equation that we have seen. Where was that equation? That dual integral equation. Yeah, this one, right? So when you add this over successive time steps, you are going to get to that equation when we apply log. Okay, so most of the log terms are used for KL divergence so that your output remains statistically just a variant of your input, not having a very good difference, right? But your input sample must be there. That is known as your reconstruction loss, which is very important. So this particular ResNet block with the attention is nothing but generating your proper reconstruction. Okay, so as you can see that this is my model which I have developed. Nothing but a conv2d having intermediate attention blocks, ResNet blocks, just one after the other. Quite a big model, but just because I have written it in this manner, it looks quite small. Okay, now the next part is having the CLIP model, right? The CLIP model. CLIP is a multimodal model which uses the diffusion. Okay, now as you know that the CLIP model is a kind of a multimodal model. That means it will need to have both your textual embeddings space as well as your image embedding space. Okay, or any kind of embedding space that you want, video embedding space or audio embedding space, whatnot. Okay, so I'm going to build it as a layer, right? I think what he has done, Franco F. Cole has done similar things. So here also the CLIP attention is a little bit different, although it is the same, but there are many tensor reshaping operations. These reshaping operations are done because in the case of images, you have different, I would say ordering. Okay, generally this is done for NCHW formatting. NCHW is a format which is used in TensorFlow by default when you are running any kind of TensorFlow image models. Okay, there are other models as well, other variations as well. I think CN, CH, NW, and something like that. So those are a little unoptimized. Okay, so keeping that in mind, the CLIP attention uses batch size, heads, number of attention heads. Okay, that means multi-head attention. How many number of heads are there in my multi-head attention? Generally, it is 12, right? You can do 24, 48, whatever, and your model complexity will go on increasing. You have your sequence length. Sequence length is nothing but your let's say, when you encode your text, right, you need to have a sequence up till how much you are going to encode it, right, and your head dimension. So in the case of your input images, you need to have a dimensions of your attention heads. It can be 64 cross 64, 128 cross 128, and whatnot. Okay, so in this case, this should be actually in the case, this particular line 13 has been taken from Vision Transformer. Okay, in Vision Transformer, when you are building Vision Transformer, your embedding dimensions should be completely divisible by your number of heads. It's not that you can do 7.677 780 or something like that, but it is recommended that you do not do this. Okay, because what happens is, whenever you are concentrating attention on your Vision Transformer, it happens patch by patch. Okay, or any kind of Vision Transformer models, right? It happens patch by patch. Okay, patch by patch means that if there is something overlapped, let's say if you do a modulus and something is overlapped, in that case, that patch will not be attended. Okay, it will waste up your CPU time, it will waste up your GPU time, okay, during computation. Okay, and you will get an inefficient outcome. So always take an absolute value which you can divide by your number of heads. Okay, this is just a recommendation, and you can follow this. You can look up through any Vision Transformer codes which is there online, anywhere. Torch, TensorFlow, doesn't matter what backend you are using. Okay, but this is the ordering which is generally followed. You have your batch size, you have your n heads, you have your sequence length, and your dimensions of your heads. Okay. Okay, so let me see if you have any questions. BERT is not multimodal, BERT is unimodal. So when we come to language models, right, large language models, BERT is a discriminatory model. In that case, it is not essentially a diffusion model. On the other hand, GPT-3, GPT variations can be thought of as diffusion models, unimodal language diffusion models. Okay, BERT is not a diffusion model, because in BERT you are doing conditional. You are not doing it. Is actually a discriminatory model. It is not autoregressive, or it is not generating anything. So you can do that. Okay, I hope that you understand what I'm trying to say. Is that this is actually a very big field, and I want to make sure that everyone understands it. Understand just the basis of it, so that it will be easier for everyone to, whenever you go through other sources, there are some good sources which I will be adding to that repo, right? Where you can go and more notebooks, okay? Where you can understand these concepts. Hugging Face is always there. They have a separate entirety module for diffusion. They have created a separate module for diffusion called as diffusers or something. So you can go through that as well. Okay. So just as I was saying, in CLIP, the attention is a little bit different, because this is not a basic attention that we are using. We have to adhere to what the ordering is: batch size into the number of heads, right, multiplied by your sequence length, and then your dimensions of your heads, the patch actually. Okay. So and then you have, just like you have any kind of transformer layer, you need to have a encoder module. Okay. And then you need to have your text transformer module. Okay, so let's understand what the encoder module is. So as you know, and I think you might have heard about the attention is all you need paper, and you have seen the BERT architecture, just a view of the transformer model, right? So in that case, you always see that there is an encoder on the left hand side of the image and a decoder on the right hand side of the image. Okay, so in the case of your BERT and your discriminatory models, any kind of BERT variations, you generally have encoder stacks. You do not have decoder stacks, right? In the case of your GPT networks, any kind of GPT language models, you have decoder stacks and not encoder stacks. Okay, so always remember that. The difference lies in the way in how they are, the token is encoded from the left to the right or from the right to the left. Okay, so for BERT, you have only encoder stacks. Okay, so in this case, for CLIP, we are going to focus on this part only. It is similar to how the architecture is similar to, you can think analogically that it is like a discriminatory BERT variation for multimodal models. Okay, so in this case, we are going to have layer normalization followed by the CLIP attention and layer normalization, and we are going to add certain dense layers, feed forward dense layers on top of it. Okay, so That's just a clip model. Now, always remember that clip has two different facets. One is your image for your image, as you saw, and one for your text. And so when you have something for your text, you need to have an encoder for your text as well. Okay. So this is where your text transformer comes into the picture. But before that, you need to have your text embeddings to pass it into your text transformer. So for that, you need to have your embedding layer. So Keras already has this embedding layer. You need to generate that embedding layer, right? You need to have your positional embeddings, and you need to, generate your, whatever, encoder. You can pass it through an encoder module. So this encoder module is the common for both your vision and your image. So if I summarize, the clip model looks like this. So you have a clip transformer, right? Centralized module, right? With transformer with attention enabled, right? So you are passing in your, I'm writing V for vision. So that means image samples, right? Image samples, image embedding spaces, and you are passing your text embedding space. Okay. So this, when you combine, right, you can generate a combined space for both you will actually return two different logits, a logits for your text and a logits for your images. Now, what you do with this logits is up to you. You can do text generation following for given an input image, or you can write some sample text and you want to generate an image. And this is also simple kind of an clip kind of a model, which is there. Okay. So the same thing is written over here in a simpler manner. Now, when we come to the diffusion part, so the diffusion model is where the centralized everything is present. So here you are calling your, here again, you have a kind of an attention mechanism. The reason is, let me show you. So this is the clip model, right? So before that, we have seen your autoencoder model. So I'm writing as AE over here, autoencoder with attention enabled for reconstruction. I'm writing it as P of 0, right? The reconstruction model. So I have this separate model. I have this separate model. Now I need to combine these two, right? I need to combine these two for each successive time steps. So yeah, so I need to combine these two for each successive time steps. So that means this is where the diffusion model comes into the play. So take from output from here, take the output from here, sample for summation of t iterations. Sample them for t iterations. So t minus 1, t minus 2, t minus 3, and so on. What you can do, you can just keep a small neural net, like a simple dense net over here, right? Or you can do any kind of variations on that dense network. Here I have done a simple ResNet with modified attention. Okay, you can keep a simple dense layer as well. So not an issue. So what you need to do is this will be your driver. This will be your driver. So which will coordinate both of your embeddings, dual embedding spaces from here, and your autoencoder construction embedding space, reconstruction embedding space. So here is your reconstruction part, which is coming into the play. And these are your text and image latent spaces, right? You plug all of them into it, and it will try to optimize this loss function, which we were seeing. So this big loss function, which we were seeing. Yeah, this, or in other words, this one. Okay, so this is from the autoencoder. These two parts are jointly coming from your dual embedding spaces, which is being squashed or processed by your diffusion process. All right, so that is what diffusion is doing in a nutshell. Okay, so this is just a simple attention block, same as what I have done before, right? And in this case, the original paper by Dickens, Soule and Dickens, right? It is mentioned here, or it is over here as well. Yeah, Soule and Dickenstein, it is there. So they use a UNet architecture for the diffusion process. UNet model is nothing but this kind of architecture, where you have your input blocks, your ResNet input blocks, and a spatial transformer. This spatial transformer is very simple. It is nothing complex. It is just a simple cross basic transformer block, which has the query key and value, right, with GEGLU activation. GEGLU is a different kind of an activation mechanism, right? GEGLU. Okay, It is also there in the layers. So it is just it is kind of a complex activation. So this is actually, if Cole has written this, it is a little bit complex to understand, because you are trying to get your, not only trying to get your GALU outputs, but also your other input samples as well. So it is a little bit complicated, but if we go back, so this uses the GAGLU optimization for your basic transformer block, right? This basic transformer is nothing but your cross attention, having this cross attention mechanism. Okay. So in this case, the spatial transformer is nothing but having this basic transformer block iterated over, I think, 12 times, right? So for UNet, they have this spatial transformer blocks one after the other. And they have a middle block, which is nothing but ResNet spatial transformer, and again ResNet block, and this goes on. Okay. So ideally, this is also known as a switch transformer, because they use a switch activation function for the UNet, right? But I'm going to keep that aside for now. This UNet model is your diffusion model that I was drawing about. So you can do actually a simple ResNet as well. So it won't be an issue. So if you remove your spatial transformer blocks, if you remove your padded conf, you can keep padded conf. You can remove your spatial transformer blocks, and still it will be a kind of a simple ResNet variant of your diffusion model. Okay, or you can use vision transformer, any kind of vision transformer. So you can do anything with it. So any kind of plugins you can add. So don't think that only I have used UNet, the paper uses UNet, so that is why I'm using UNet, but you can do anything. Okay. And what you sample from this log, entire loss, right? The combined loss that you get, you try to optimize this loss. This big loss, I'm not writing it here because it is quite big to understand, to write it down. But this is the loss that you're optimizing. Okay. This is the loss that you're optimizing. And when you optimize this, now what you are doing, think like this: when you're optimizing this loss, you already have the reconstruction. That means that whatever text I'm writing, text is my input latent space, right? So my text, what am I writing? Your autoencoder should take that into mind, that my output image should resemble my input text. It should not be diverging from it. Okay. The clip transformer has the responsibility to actually generate coherent embedding spaces for your text and images. And the diffusion model, that is your UNet model, has the responsibility to merge them in such a way so that this function can be optimized in real time. Okay, the reconstruction loss should be taken, and also the clip embedding spaces should be taken. Okay, diffusion does this, UNet does this for every successive time step. So this is just the diffusion model. Now stable diffusion is the interface where this is actually happening, which is calling this function, this generate function, right? For number of time steps that you want to have, right? How many time steps you want to iterate on, how many steps, what should be your generating principle, right? So all of those are, if you want to generate in a, let's say, I forget the term, what that is called. How, what is the term that you call? Like you do a generation like this, you branch like this. I'm forgetting the term. It's coming to my mind, but not to my mouth. So yeah, so this kind of branching that you see in generative GPT or any kind of generative sampling, you can do over here as well. Okay, so this is done for successive iterations. How many iterations or time steps you want to run your diffusion model, UNet model. Okay, this decoder is nothing but your UNet decoder. Okay, this UNet decoder will generate the final output logits. Okay, and then you can do, you add your noise and you perform that kind of optimization. Actually, the UNet model is itself capable of generating a good output latent space, provided your clip embeddings and your input sample from your autoencoder. Okay, so that is what is happening in a nutshell. And when we go to this part, is that this is actually the interface. This text to image is the interface, the image height and image width, right? And I'm calling this generated.generate, right? This table, which is coming from this stable diffusion or this particular function, this generate function. You can take a look. It is there in GitHub, right? How it is happening. So the flow, how it is happening, just giving an outflow. right? First you encode your prompts. Prompt means your text, right? And you take your image tensor, right? And you pass it into your where was that? That decoder. The self.decoder is your effective UNet decoder. So you can think in such a manner that if I go to this image, this is actually an encoder transformer, right? I'm writing it as E, and it is taking from your reconstruction loss from your autoencoder, and it is doing the deconstruction or your decoding over here from in the UNet or any kind of model that uses a diffusion. So this diffusion part or this diffusion model is doing your decoding, okay, to give you a final representation. All right. So this is the idea behind how diffusion models, multimodal models work. Okay. If you change the number of steps, the t over here, the t in this equation, this summation t will reduce, and if you reduce, it will take less amount of time to train. So it is quite obvious. So this is image to image, text to image. Okay, trust me. So this I write Bin Laden dancing with Hitler, just a kind of a fun. I'm not sure what they have created. Not sure, but seems quite odd to me. You know, even if you try to do for more than 50, 60 iterations, right? Maybe 150 iterations, you will try to get something which is more believable. So this is one model, text to image. You have several other models which I have added over here, which is from OpenAI, right? Text to image, and these are all having the same code base. These are all having the same concept that I have told. So Glide, the text to image that I have talked about, this is nothing but Glide. They have given a separate name for it because they have trained it on they have changed the reconstruction loss to make it more photorealistic, to make it more realistic rather, and they are more or less they're using the same architecture. They have a clip guided, which is nothing but using the clip architecture that they have written. So you can go through this part of the code as well, written in PyTorch. This is actually the Glide paper, which is the source of your text to image. So Glide is the source of your text to image, clip generation, whatever multimodal models that you see. Okay. If you get time, or if you have scope, try to understand why Gaussian noise is used. Okay, because that is very important concept mathematically. Why Gaussian noise is used? Good to have concept. Good that if you know that. Okay, why not any other? Why cannot I have a Poisson distribution and only a simple Gaussian distribution, right? So you can. It is there in the readmes and in the things. If you have the mathematical aptitude, you can just understand it. Okay, so that is what I wanted to cover mainly. Since time is running out, and I also wanted to cover some question answers because it is very important that you understand. So first of all, this diffusion model is not at all beginner friendly. The reason is because, as you might have understood, diffusion is based on a probabilistic model, right? A probabilistic Markov chain model. So and taking that part from your Markov model, Markov chain theory to your code, right? And not only building a statistical model, but actually you are building a very complex neural network for multimodal models. So in that case, it becomes a bit difficult to understand. Now, the first way to tackle this is, I would say, go through my code, or go through Fcole's code, right? Understand like the flow, how it is happening, flow by flow. First, text to image is called, which calls in my stable diffusion, right? Stable diffusion is a driver interface which calls your diffusion model, right? So whenever you learn about diffusion models, try to think it from a wide angle. So this is my driver diffusion model, right? UNet or something like that. And it takes your embedding spaces from any multimodal model. I have used Clip. It can be any multimodal model. It can be DALI, or it can be anything, right? It can be anything. So if you replace this multimodal model with a single transformer model, let's say language transformer model, let's say BERT, or GPT, Bert or Albert or P5, right? So in that case, you will have only text to text, so textual kind of generation using diffusion, right? So you can do anything with it. So these are all pluggable parts. So whatever modalities you choose, right, you can plug that in. I just took a sample example of multimodal models because that is trending as of now. And I wanted you to understand this at a broad concept because the code is available everywhere, right? So there are again certain blocks of code which I have omitted because it is very complex. So you can take time to understand it. But the first way is to understand or have the view, go through the blocks and have the view of that particular aspect. Okay, the broader view, and then go through the code one by one function at a time, and you will be able to understand at a much easier way. Okay, I hope that makes sense. Could you show their paper again? Yes, Soul and Dickenstein, I think so. It is there. It is there in the it is there in the link in the paper, so you can go through them. Soul et al. Yeah. So there is one by Soul et al. And there is one by Ho et al. So Ho et al. Uses denoising factor. Okay, so that is beyond the scope, right? So yeah. So is there any other questions which you have? I hope I answered your question on this part, because I know that it is a little bit difficult to understand. First of all, the workflow I would suggest is, if you are new to attention and transformers, try to understand attention and transformers, try to understand CLIP, then try to understand your autoencoders, and then try to understand diffusion models. Is stable diffusion equally capable? Yes, yes, yes. One short word answer is yes. The reason why is because the initialization function that you use, I told that Gaussian, you use Gaussian, right? You use Gaussian. It does not matter what optimization you use. Let's say you use Fisher optimization in Hilbert space. So in that case, it will run fine. Okay, so stable diffusion, that is the reason why stability has been added, because you are kind of modulating a Markov chain with Gaussian space as your simulator, right? So it is very, I would say, it will run for all, right? It is equally capable in every space, every real space. That is why it said that it is capable in every real space, right? So I hope that clears this question. Thank you. Have a great weekend. Bye.